Thank you, the organizers, for inviting me to this nice workshop. I think it's going really nice. Thanks. Also, well, I'm the PhD student of Professor Thomas Fredriksen at the Donald International Physics Center. And I'm going to talk about electron spin states in graphene nanostructures and how we can study them with the Hubbard model. So this is the outline of my talk. I'm going to give a brief introduction of how magnetism can be induced in graphene nanostructures and how we can study it with the Hubbard model. Then I will explain a little bit how one can use our implementation of the Hubbard model to find the self-consistent solutions for different systems, depending on the boundary condition. Then I will show an example of some spin transport calculations for multi-terminal devices that we did in the past. And then I will conclude with some final remarks. Okay, so first of all, graphene is not in principle a magnetic material. However, there are several ways in which we can induce magnetism in graphene nanostructures. For starters, the Lip's theorem states that the total spin of a bipartite lattice is proportional to the lattice imbalance between the A and B sublattice. Here at the right side of the screen, I show an example of a triangular shaped graphene nano island whose total spin grows with the size of the structure. This can also be extended to having local sublattice imbalance in a structure. For instance, here I show a very known example, which is the zigzag graphene nano ribbon, where the local sublattice imbalance that is present at the zigzag edges of this structure hosts localized magnetic moments at the edges of the ribbon. Of course, the presence of atomic defects also generate localized states that give rise to localized magnetic moments. On the other hand, with the onset of bottom-up techniques like unsurface synthesis, now all these scenarios that I just showed can be experimentally produced with a careful design and atomistic precision. In particular, really large systems can be now synthesized, so we need a model that can handle with such extended structures. For instance, the model that I will show in this talk allows us to run calculations locally in our machines and is Python-based, which is really handy in my opinion, and can obtain the self-consistent solutions for large structures in a matter of seconds or minutes, depending on the size of the structure, and can give results that are comparable to other more accurate theoretical methods, such as density functional theory, and so on, if one uses the correct tight binding parameterization, as Gaetano nicely explained yesterday in his talk. Okay, so as I said, one way to study the magnetic features in graphene nanostructures is by employing the Hubbard model. This is the easiest way in which we can include electron-coulomb interactions in the model. This Hamiltonian is composed by two terms, the kinetical term, which is the pure tight binding Hamiltonian part that you are all familiar with. It just describes the tunneling of electrons between neighboring atomic sites and is modulated by this hopping parameter. And the interaction term, which accounts for the Coulomb repulsion that two electrons are going to feel when they try to occupy the same atomic site. Despite the apparent simplicity of this model, it cannot actually be analytically solved for most of the cases. So what we can do here is to approximate this product of operators, which is what is giving us the problem here to solve the Hamiltonian, with the following expression, where we have neglected spin fluctuations. And with these ingredients, we now can solve the Hubbard Hamiltonian in the mean field approximation and find a self-consistent solution by iteration method. Okay, so before I move on, I wanted to show the front page of our GitHub repository, which you can find online in GitHub. It's called the Hubbard package, where you can always download the latest version here. And then you can always check the online documentation where we have a lot of information of all the classes and methods that we have implemented within this package. Okay, now I will continue to explain how we can use the Hubbard package to find a self-consistent solution for different systems depending on their boundary conditions. And I will start with the case of isolated structures because it's the simplest one. So the iterative process begins by taking an input Hamiltonian and some input spin densities. Then it diagonalizes the Hamiltonian. It builds new output densities from that diagonalization, and it takes those spin densities to update the Hamiltonian. Then two things can happen. Either the difference between the output and the input densities is smaller than the threshold, or the difference between the output and the input densities is larger than the threshold. In the first case, we will have found a self-consistent solution. In the other case, the self-consistent process has to start over by setting the output densities as the new input densities and just go again until it finds this step here. Here I show an example of the spin polarizations that we obtained using the Hubbard package for a particular molecule that was experimentally synthesized by the group of Nacho Pascual in Nanogune in Donostia, San Sebastián. I'm not going to go into the details here, but I just wanted to show you the comparison between our theoretical predictions or where the spins localized in the molecule compared to the experimental images. I think we all agree that the resemblance is very good. The agreement is very good between these two images. At the right side of the screen, I left some pseudo code lines to explain how one can actually use the Hubbard package to run such calculation. This is all Python, okay? Okay, so basically we will start by defining the tight binding Hamiltonian of the structure for a specific geometry and set the dimension of the Hamiltonian to 2 because we want a spin polarized Hamiltonian using CISO, of course. Then we will define the matrix element of the Hamiltonian and so on, as always. Then we can build the Hubbard Hamiltonian by passing the tight binding Hamiltonian, the desired on-site Coulomb repulsion, the temperature of the system, and the total number of up and down spin components. Then, before convergence, we need to initialize the spin densities. And we need this spin density distribution to break the symmetry between up and down spin components. Because if we start the convergence process with some spin density distribution that is equal for up and down spin components, then the code will not be able to find a symmetry broken solution, which is what we want. So that's important. And furthermore, if we know or have an intuition of where the spins should localize in the molecule, we should use that intuition because it will probably save a lot of time in the convergence process. So if the initial spin densities is closer to the self-consistent solution, it would take much less iterations to obtain such a solution. So that's also handy. Another interesting feature of the Hubbard package is that we developed a plot class for the mean-field Hubbard Hamiltonian. So you can find in this class of the package a lot of different methods to plot interesting physical quantities, such as the spin polarization, the charge distribution, the spin wave function, and so on. We have also developed a function in which we can use the spin densities, the output spin densities of the final self-consistent solution of the mean field Hubbard as the input for a more accurate spin polarized siesta calculation. So it can write the spin densities as an FDF block for a spin polarized siesta calculation, which I think it can also save time in that calculation. Okay, so here I show you also a comparison between our calculations with the mean field Hubbard and with other more accurate density functional calculations, in particular in this case with siesta. And as you can see here, we can also find a very good agreement between these two calculations. And I think from these two slides, we can conclude that the mean-free Hubbard model is working perfectly nicely for these sp2 carbon systems. This type of example of a molecule you can find in the tutorial 1 of the mean-free Hubbard package. Okay, I will continue with explaining how we can find the self-consistent solution for a system with periodic boundary conditions. Okay, so going back to our self-consistent process, generalizing the implementation for systems with periodic boundary conditions is pretty easy because we only have to do the same as before, but for the log Hamiltonian. So now we would have to diagonalize the Hamiltonian for each k point in the Brillouin zone and then integrate to obtain the spin densities. But the rest of the process is exactly the same as before. Here I show an example of a calculation of a one-dimensional zigzag graph nanoribbon, periodic zigzag graph nanoribbon, which is a typical example because we know that this structure hosts localized edge state that tend to polarize when we include electron interactions in the recipe. For instance, that is the reason of why the band structure of the polarized structure opens a band gap around the flat band area that belongs to the band structure for the unpolarized case. This band gap, which is called the correlation band gap, is proportional to the Coulomb repulsion parameter. At the right side of the screen, I also left some code lines to explain how can we actually use the Hubbard package to obtain such a calculation. So as before, we start with a Hamiltonian and we do the same as before physically. The only thing that changes is that when we build the Hubbard Hamiltonian object, we have now to pass the number of key points along each direction in which we want to sample the Hamiltonian during the convergence process. So say we have a system that is periodic in 2 dimensions, then we should set this number or well, say the system is periodic along the X and Y directions, then we will have to change this number and this number to a larger than 1 to sample the Hamiltonian along that directions. And if the system is not periodic along, say, the Z direction, then this number can remain to 1. And something that I didn't tell before, sorry, I forgot. When we go to the converge method here, that will iterate the Hamiltonian up to a certain tolerance, importantly, we have to pass a function that will tell the code how the spin densities are going to be obtained during the convergence process. For molecules and periodic systems, this function is the same because this function is already generalized for accepting systems with periodic boundary conditions. Okay, I think I didn't forget anything here. Now I am going to do a small break and we come back after 2 or 3 minutes.
Sophia, there's one question for you.
Okay, I think I have to stop sharing to, no?
You don't see the question.
No, I said, yeah. Could you please clarify the difference between tight binding and Hubbard models? I mean, the tight binding usually doesn't account for Coulomb repulsion interactions. It's just, you don't solve the tight binding Hamiltonian self-consistently. Yeah, so the second question is very interesting. I missed some part of the talk. How do you choose the Hubbard U value? This is very tricky. It's like choosing the parametrization for a tight binding calculation. I mean, you have to know your system and compare with experiment. This is a semi-empirical value, and you have to choose a value. I mean, on one hand, it cannot be in a regime which is much, much larger than the hopping parameter, for instance. I think that's something to take into account, because otherwise you would be in the strong correlated regime. But the value of the U is not really easy to give a straight answer here, because it depends a lot on your system. And probably, for instance, if the system is on a surface, on another surface, the interaction with the surface will screen more or less that value. So probably even in the same geometry or molecule will change if you compare to one experiment or another. This is the same thing. Well, the question here is, what about the intersite coupling? So this is the same thing as for the U value. You have to choose a parameter that describes your system, knowing your system and comparing with other more accurate descriptions, such as density functional theory or other models that allow you to describe your system with that parameterization. But depends on
the intersite Coulomb repulsion, no?
Well, the question is, what about the intersite coupling?
Coulomb coupling, the repulsion between different sites. That's not considered here.
Ah, I understood. Okay, the coupling parameter. Yeah, that's not, well, we are actually working on that in there is a branch in the GitHub repository when we are working with intersite Coulomb repulsion, but it's still not out. It's a working process. Another question here, in your code, can we use more than one U parameter, the V parameter? That's a kind of hopping of Hubbard parameter. It's implemented. So far we have implemented the implementation that is in the master branch, and in the latest version allows only to pass one value, a float that is equal for all the atoms. But we are very close to releasing a new implementation where you can pass different U values depending on the different atoms that are present in the structure, and also different values that your atoms with different orbitals may have. So yes, that is going to be soon released. For your study of nanographen systems, how does the Hubbard model compare with DFT, say bank structures? Well, we have performed comparisons for the zigzag graphene nanoribbons or anchor graphene nanoribbons and so on. And the comparison is pretty good. I mean, I would say as good as a tight binding calculation would compare with a DFT. So it probably, it for sure will depend on your tight binding parameterization. And I would say that the biggest change when adding a Coulomb repulsion happens around the Fermi level. Could one use as the input Hamiltonian, a DFT tight binding parameterized Hamiltonian, and then add to such HO with the Hubbard term? Yeah, so this is what I was mentioning before, the new changes that we are going to release soon. Will allow to pass a Hamiltonian for with atoms with different orbitals, where you can set the Coulomb repulsion for each orbital. So you should be able to pass your DFT Hamiltonian and add just the Hubbard term. Yeah. There is some comment I don't understand. Also called J parameter in some references. Your Hubbard Hamiltonian in your code can work with Vanier 90 parameters. I'm not familiar with Vanier 90. I guess if you can extract the Hamiltonian, you could do the same as with a Hamiltonian. I mean, and if you can extract it with CISO, which I'm not sure if you can. Yeah, Nix is saying yes, so yes. Then you should be able to do the same as the question of Xavier asked. Okay, there is another question. If we increase the cutoff radius of an atom siesta file, much different from the pseudopotential file, does it take care of bandgap estimation? Also, does it change the physical meaning of the atom? Sorry, I'm not familiar a lot with siesta pseudopotentials, and maybe another one can answer this question. I think it's not very related to the Hubbard
session. Okay, so should we have a short break?
Okay, I will start in 3 minutes. 2-3 minutes.
3 minutes, okay.
Okay, so well, now I will continue with explaining how we can find a self-consistent solution for systems with open boundary conditions. So, well, first of all, what is an open boundary? What is an open quantum system? So we already know this from previous talks in this workshop, so I'm not going to go into deep details here, but I want to introduce a little bit the concepts in this context. So imagine that we want to obtain the mean field Hubbard Hamiltonian for an infinite system with a defect. Well, what people typically do is to apply periodic boundary conditions to the defect and find a self-consistent solution for the block Hamiltonian with periodic boundary conditions. But that's not what we want here, because we want the defect to appear only once in the structure. So what we can do is to use the non-equilibrium Green's function formalism where we can compute the Green's function of the device, from which we can obtain the density matrix, from which we can extract the spin densities for this open quantum system. So let's start by defining the different parts that take place in this calculation. So this structure can be divided in 2 parts. The electrons, so the periodic part, which are periodic leads that grow towards some semi-infinite direction, and then the device region or scattering area or central area or whatever you want to call it that contains the defect and is coupled to the semi-infinite leads. Then, as Nick already explained, you can couple the leads to the central region by using the soft energies of the leads. And then we can obtain the Green's function per speed channel of the device. Then from the Green's function, we can use the Green's function to obtain the spin densities for this device. And use that in each iteration to obtain the self-consistent solution for this system. So going back again to our self-consistent process, then we only have to substitute the way in which we obtain the density, the spin densities in each iteration, which for this case, we will use the Green's function, which we will iterate along an energy contour, which actually is extracted from a transistor calculation. And from this integration, we will obtain the density matrix, and from it, we can extract the spin densities in each iteration, and the self-consistent process remains the same as before. So this new implementation is in a particular class of the Hubbard package, which is the NEGF class, which I will show now, which contains this implementation with the Green's function formalism. Okay, so how can we actually use the Hubbard package to obtain the self-consistent solution for an open quantum system? So as similarly as in the case of Transiesta, we first have to converse the mean field Hubbard Hamiltonians for the periodic electrodes. So we will define the unit cell of the electrodes and converse the mean field Hubbard Hamiltonian just as we saw before in the first part of the talk. And then we can continue with the different steps for the device calculation. So as before, we start by defining the Hamiltonian, the tight bending Hamiltonian of the device for the device geometry, and don't forget to set the dimension of the problem to 2 because we want a spin polarized Hamiltonian. And then we can define the Hubbard Hamiltonian object again by passing the tight binding Hamiltonian for the device, the on-site Coulomb repulsion parameter, and the temperature of the system. And if we want to stay in the equilibrium regime, these two parameters should be the same as the one that we use in the convergence of the electrodes. Then we have to initialize the spin polarization as before. And then we have to build the NEGF object for the device. So to do that, we just have to pass the Hubbard Hamiltonian object for the device, a list of containing tuples with the already converged Hubbard Hamiltonian for each electrode and each semi-infinite direction. And this can be as long as many electrodes you have in your system. And then a list containing the atomic sites that correspond to where the electrodes are mapped in your device. And by building the NEGF object, it allows us to use the methods with the Green's function formalism to obtain the spin densities for the device. So when we call the method converge here of the Hubbard Hamiltonian class, we only have to pass the function from the NEGF class that tells the code that now the spin densities are going to be obtained from the Green's function of the device. A nice and interesting usage of our implementation for to solve open quantum systems is the possibility to study multi-terminal devices. A line of research that we have been developing these past years is the study of 4-terminal devices that are formed by two graphene nanoribbons crossed with an intersecting angle of 60 degrees. Because the symmetry of the honeycomb lattice at this rotation angle, there is a perfect matching between the bottom and top sublattices. So this translates in that there is an enhancement of the transfer process of electrons between the two ribbons. And this also translates in that we can find really nice transport properties for these 4-terminal devices. For instance, it has been shown that if one injects electrons into the device, they will be equally split into 2 out of the 4 terminals without reflections. So in these conditions, the device will work as a perfect electron beam splitter. So now we can ask, what happens if we include electron interactions in the recipe? So now with our implementation of the Hubbard package with to solve open boundary conditions, we can obtain the spin densities for this 4-terminal device, as I show here, and obtain spin resolved transport properties of this device. For instance, here I show the spin resolved transmission probabilities that we obtain for this 4-terminal device. And we observe here, well, first we compare here the case of the unpolarized case, which is this dashed dot line, and the case of the polarized case, which is the solid line. And you only see 2 curves difference because the transmission probabilities for both spin channels is the same, so the lines overlap. So we can observe 2 things here. On one side, that the beam splitting effect survives the presence of Coulomb repulsions. And on the other hand, the only things that seems to be different from the unpolarized case when including electron interactions is that we now observe the band gap opening, the correlation gap opening that corresponds to the band structure of the polarized zigzag graphene nanoribbon. So I think with this I can conclude. We have learned that the Hubbard model in the mean field approximation yields a very good description for this sp2 carbon systems, as I showed the comparison between our theoretical results with this package and experiments and other more accurate theoretical methods. And also by choosing the appropriate method in which we can obtain the spin densities, we can solve a lot of many different systems. For instance, molecules or periodic structures or systems with open boundary conditions. Please visit our tutorials where you can play around with our Hubbard package in these 3 different examples. Please note Nick's comment in Discord that you should download the 2nd version of tutorials. And lastly, I showed that now with our implementation of the NEGF class, by being able to obtain the spin densities for open quantum systems, we can also obtain the spin transport properties, which is very interesting. And also, I would like to thank all the people that have participated in all the projects that I mentioned in this talk. In particular, thank you, Nick, for all your participation in the development of the Hubbard package. Thank you all for your attention.